Hi, welcome to this lecture on basic data structures. Here's the outline for this lecture. We'll start by talking about some Java preliminaries, and then we will discuss a data structure called linked list and how you perform various operations on a linked list. And then we will discuss three fundamental or basic data structures called bags, queues, and stacks. And then we will discuss how you implement their APIs using two different approaches. One using the linked list data structure and the other using a static array in Java. All right, and then finally we will discuss the performance characteristics of the different implementations of bags, queues, and stacks. So that's the plan for the lecture. Let's get started. So in Java, there is a mechanism called generics or parameterized types that allows you to implement collection data types or data structures that can store any type of data. All right, so let me illustrate this via an example. So here in this code, what you see is the use of a collection ADT called stack that we're going to discuss later. Right? So in the first statement, we declare a stack object called S1 as a stack of string objects. Okay, so S1 is a stack that stores strings, and this is basically the syntax that you use to create a stack of string objects. So in the angle brackets, you specify the type of the data that you're going to store in the stack. All right, so that's part of the syntax. Other than that, it's the good old syntax for creating an object of any type. You basically call the constructor. So here we are calling the constructor of stack. Okay, so S1 is basically an object of type stack, and S1 is a stack of string objects. And then what we do next is we create another stack object called S2 as a stack of date objects. So it is the same data type that we use to now create a stack of date objects. All right. So what you put in angle bracket is basically the type of the data that you're going to store in the stack. Other than that, it's the same syntax for creating an object. Okay. So we have two stacks now. S1 is a stack of strings and S2 as a stack of data objects. And that's what we are talking about here. And so Java, via this mechanism called generics, allows you to implement collection ADTs that can store objects of different types. Okay, and then what we do is we simply use the methods from the stack API to work with those stacks. So we push the string test into stack S1, and then we push a date object. So this is a date object into the stack S2. Okay, so it's the same push method from the stack API, but in the first instance, we are pushing a string using that method into the S1 stack. And then in the second case, we are pushing a date object into the S2 stack. Okay, and then finally, what we do is we pop S1. So we get the top element of the stack S1 and store it in the variable S, which is of type string, because S1 stores string objects. And then we pop the top item from stack S2, which is a date object, and we assign it to D, which is declared as type date. Okay, so this example just shows you how you use the same data type, a collection data type, to store objects of different type. And this is made possible by Java's generics mechanism. Okay, now generics are reference types. Okay, what that means is a collection ADT can only store objects or reference type data. Okay, and since that is the case, since generics can only, since collection ADTs can only store objects, Java allows generic code to be used with primitive types by automatically converting them into their corresponding reference types using autoboxing, which we discussed before. And it also allows you to go from a reference type to a primitive type via what is called auto unboxing. Okay, so Java sort of like lets you does this conversion implicitly for you. Okay, and that is illustrated in this piece of code here. Okay, so what we are doing here is we are building a stack as a stack of integer objects. Okay, so notice that in the angle brackets we specify the type of the data that goes into the stack, and in this case we are saying the type is integer objects. And since stack is a collection ADT, and since we are using generics to implement it, you cannot store a primitive int inside of this data type. So that's not allowed. But you can store an integer object. Okay, and that's what we're doing here. So we're saying stack is a stack of integer objects. Okay, and you mention integer on the right hand side as well. That's part of the syntax. Okay, and then what you can do is you can push an integer into the stack by saying stack.push. So you're making a call to the push method from the stack API to push this item into the stack. Now notice that this is a primitive int 42, but Java supports what is called autoboxing, which implicitly converts this primitive int into an integer object. Okay, so you don't have to do that explicitly. Java will do it for you. That's autoboxing. And then later on, if we go about popping an item from that stack, what comes out is an integer object. Okay, and then here we are assigning it to a primitive int, and that is made possible by the auto unboxing operation. So Java will implicitly convert the integer object that is returned by this pop call into a primitive int. Okay, so Java lets you convert these things sort of like seamlessly, right? Okay, now iterable collections are ones that can be enumerated or iterated over using the enhanced for loop or the for each statement. And this is something that we have discussed before when we talked about the iterable or the iterator interfaces, right? And here is an example. So later on, we're going to talk about a collection ADT called bag. Okay, so you can create an object of type bag as such. And in this case, numbers is an object of type bag that stores integer objects. Okay, and we will see this later that bag is going to be an iterable collection, meaning you can iterate over this object, this iterable object, using the enhanced for loop. Okay, so let's say after building this bag object, we throw in a whole bunch of elements into it, a whole bunch of integers. And then if we want to print out the items, the elements of bag, we can use the enhanced for loop, okay, which is what we are doing here. So this is the for each statement where we say for each integer in the iterable object, so number says an iterable object of type bag, we're saying for each integer in that object, simply print out that integer, okay. Now here again, there is auto unboxing going on because each element in numbers is an integer object. Okay, but notice that we are referring to those using a primitive int. But Java knows how to deal with this. It'll implicitly convert each and every element here, which is an integer object, into a primitive int. Okay, and that's what gets printed here. Okay, and then we also know that this code implicitly translates into this while loop. All right, so it is as if we first get an iterator out of numbers, which is assigned to this variable iter, and then we have this while loop that says as long as that this iterator has a next item, get that item and print it out. Okay, this is something that we are familiar with. Because since numbers is iterable, it supports the iterator method, and that returns an object of type iterator. Now iterator itself supports two methods, has next and next, okay, which is what are used here. Okay, so let's continue. Now let's talk about a data structure called a linked list, which is an extremely important data structure, right? Now a linked list has a recursive definition, okay? So it is a recursive data structure that can either be empty, which is denoted by the keyword null in Java, or it can be a reference to a node that has some item stored in it. This is the data that you would like to store. It's a generic item, meaning it can be an object of any type. And in addition, that node has a reference to the rest of the linked list. Okay, so that's the recursive definition. So you may want to think about a linked list as being either null, which I'm denoting now with just a dot, or it can be a node, okay, with two things. It can have a generic item, and that item has a generic type which I'm denoting as capital T in angle brackets. So item can be an object of any type. So this now is a single node, and then in addition, that node has a pointer to the rest of the linked list. But because of the recursive definition, what is the rest of the linked list? But that in itself might be another node, okay, with an item and with a pointer to the rest of the linked list, and so on and so on and so on. And then you might have a node at the very end, and that would have an item itself and a pointer that is null. Okay, so this whole thing is what we call a linked list, which is nothing but a series of nodes. So starting from the first node, you can get to every other node following these pointers. Okay, so that's a linked list. And in Java, a data structure like this would be represented very easily as a private, as a class, right? And we typically implement it as a private class, because it usually serves as a helper for other things. Okay, so this then is our definition of a linked list. And an object of this class node represents one of those boxes, one of those nodes in the linked list, all right? Which has two things in it. It has an item, which has a generic type. So it can be an object of any type. And then it also has a pointer that we call next to an object that is also of type node. Okay, that's the recursive definition. Okay, so an object of this class basically represents a node in the linked list. It has a generic type, it has a generic item, and it has a pointer to the next node in the linked list. Okay, so that's how we define a linked list. Now, once you have a linked list, how do you traverse it? Because that's something that you do a lot. For example, you would like to just walk through the list and print out all the elements, all the items in sitting inside of the nodes in the linked list. How would you do that? Well, you can very nicely do it using a for loop, all right? So let's again, take this. Think of this picture. So here is my linked list. It has a first node, all right, and it has an item, and it has a next pointer to another node that has an item and a next pointer to another node that has an item and a next pointer, and so on and so on and so on, all the way up to the very last node that itself has an item and a pointer to null. Okay, now the question is, what if you want to print out all these items in this linked list, where first refers to the very first node? Well, you would use a for loop like this. Okay, so let's try and understand this loop. So you say the first part of the for loop, where you initialize things, you say node x. So x is simply a variable of type node. You say x is whatever first is. So x is basically pointing to this guy, this node, right? And then you say for the Boolean condition, you say as long as x is not equal to null, meaning as long as you're not at this guy here, simply update x as the next value of x equals the current x's next. Okay, so the first time around x refers to this guy here. Okay, and then what you do is you check if x is null or not. Well, it's not null, it's the very first node. So in that case you say x equals x dot next. So now the new value for x is, you simply say x is x dot next. So now x points to the second node, right? And then you do whatever needs to be done here in the body. For example, you might print x's item, right? And then you go back and you update x. So the new value for x is next. So this guy's next is this fellow. So x now becomes that. And you check if x is not equal to null. Well, it's not equal to null. So you do something, right, in the body of the for loop, and so on and so on and so on. And at some point, x is going to point to this node here, and it's still not null. So you carry out what's in the body. And then you say x equals x dot next. But whose x is next? It's null. So the new value for x is null, and that's when this condition becomes false. Okay, and you're out of the for loop. So that's how you typically traverse a linked list using a for loop. Okay. Okay, so now that we have a definition of a linked list and we know how it's represented in Java, let's talk about how you build a linked list and how you perform some basic operations on it. All right. So the first thing is, how do you build a linked list from nothing? So you have null for a linked list. How do you end up with a linked list that has one node in it? Well, here is the code that will do it. Okay, so you would say first, which is of type node, equals new node. Right? You simply call the constructor of the node data type. Now remember that in Java, when you have a type that doesn't have an explicit constructor, you get an implicit constructor, no argument constructor for free. All right? So it is as if you have a constructor that takes no argument inside of the class data type. Okay? So you call that constructor and you build yourself a node object. When you do that, what you have in memory is something like that. All right? So first points to this node. There is nothing for item, and then this guy simply points to null. And then what you do in the next line is you update the item. So you say the item instance variable of first is simply the string 2. All right? So that's what inserts the string 2 in there. Okay. Now remember that item is a generic. So you can store an object of any type in there. And in this case, we are building a linked list of nodes that contain strings for their items. Okay. All right. So once you do this, you have a linked list whose item is the string 2 and whose next is null. All right. So this is now a linked list with one node in it. And the linked list is pointed to by this variable first. Okay. Now let's say you want to create another node and link the first one to it. All right. So how do you do that? Well, this is how you would do it. You would create a new node called second, and when you do that, you have something like this in memory. So this points to null, and there's nothing for item, and second is pointing to that. And then you say second dot item is the string b. So that's how you get b in there for the item of second. And then you do something interesting. You say the next of first, which was null, to be whatever second is pointing to. So second is pointing to this guy, but now you say first's next, which is this guy, is whatever second is pointing to. Okay, so it's no longer null. And that's how you end up with something like this. So first now points to this node, whose next points to this node that you just created. Okay, so now what do we have? We have a linked list that has two nodes in it, right? What if we want to add one more node? Well, that's exactly the same idea. So you create a third node, and at that point the third node is going to look just like that, with its next being null. So this is now third, And then you say third's item is the string or. So that's how you end up with or in there as a string. And then you say seconds next is third. So then this seconds next points to whatever third was pointing to, which is that node. So now what you end up is with a linked list that has 3 nodes in it. The first node has the item 2. Its next pointer is pointing to the node, which is this guy, whose item is B, whose next is pointing to this node here, whose item is OR, whose next is null. Okay, so it's a linked list with 3 nodes in it. All right, now that we know how to build a linked list from scratch, let's talk about how you would insert a node at the beginning. All right, so let's say we have that linked list from the previous slide with 3 nodes in it, and that we want to stick a new node at the head of that linked list or at the beginning of that linked list. So what is the code that will do that? Well, this is how you do it. You first say, you create a new pointer called old first of type node, and you make that point to whatever first was pointing to. So now both first and old first point to the first node in that linked list from the previous slide. Okay, and now what you do is you create a new node called first. So that sets up this node whose item you set to be not, which is this guy here. Right? So that's a completely new node. Okay. Now you want to make this node be the first node of this linked list. So what do you do next? Well, the step is obvious. You want to make this node's next pointer to be this node. Well, how is that done? Well, you simply say first's next. So first's next is this fellow here. You say that's simply whatever old first is pointing to. So that establishes this pointer here. Okay, and you end up with this 4-node linked list. So notice that you started with the 3-node linked list and you've managed to insert a node at the head or the beginning of that linked list. Okay. Now what about removing a node from the head of the linked list? So let's say you have the 4-node linked list from the previous slide, which is this guy here, and that you want to take out this first node. So how do you do it? Well, first is already pointing to the first node in that 4-node linked list. So all that you need to do is say the new value for first is whatever first's next is. So first dot next points to that. So if I simply say first equals first dot next, first now points to that guy. Okay. So, and that has the effect of excising this node. And notice that you no longer have anything pointing to this node, but the Java garbage collector will eventually free that from memory, right? So the end result, end effect of having this statement is that the new linked list is now this guy here with the first node removed. Okay? So removing from the beginning is an extremely straightforward operation. You just follow this approach. Okay. What about inserting at the end of a linked list? So let's say we have the linked list from the previous slide, which is this guy, and first is pointing to the first node in that linked list. What if we want to insert something at the very end, something there? Well, this is how you would do it. In this case, we are also assuming that there is a pointer called last, which is pointing to the last node in the linked list. Okay, so we have 2 pointers, first pointing to the head of the linked list, last pointing to the tail. So how do we insert at the very end of the linked list? Well, what we do is we create a pointer called old last, which also points to what last is pointing to. So you have both old last and last pointing to this node. And then what we say is we create a new node whose item is not. Okay, so that's the node that you want to insert here. It's a new node that's pointing to null and whose item is not. And then all that we have to do is establish a link from here to this new node. Well, how do we do that? We simply say the old last's next. So old last is pointing to this one. We say its next is simply whatever last is pointing to. Okay. So that establishes this link. So old last's next, which is this pointer, we're saying that is now equal to whatever last was pointing to, which is this node that was created from here, and that gives us this link. So what we end up with is this 4-node linked list. All right. Okay. So those are the basic operations on linked lists that we are going to be interested in. So we know now what a linked list is, and then we know how to represent it in Java. We also know how to traverse a linked list, and then in addition we know how some of the basic operations are carried out on a linked list, such as insert at the beginning or remove from the beginning, or insert at the end. All right. So now let's talk about the 3 fundamental data structures, which are bags, queues, and stacks. And we're going to start with bags. So bag is an iterable collection. It's a collection data type, collection ADT, and it's iterable, and it provides clients the ability to collect or store items. All right. So it's basically a data structure that allows clients to store objects of any type. So it's going to be generic and iterable. Generic meaning that it's going to store objects of any type, and iterable meaning that the client will be able to iterate over its elements. So here is the API for the bag data type. So you have a constructor that lets you build a bag object that can store objects of any type. So this item in angle brackets denotes that it is a generic. And notice that item is just a name. You could have called it whatever you want. Some people insist on calling this just capital T. Okay, but anything that you put there in angle brackets makes that type a generic. Okay, so bag is now a generic collection ADT. Right. So with this constructor, you can build a bag object, and then once you have a bag object, what can you do with it? Well, you can check if it is empty or not. Meaning, does it store anything yet? If it stores something, it's going to return false, and if it doesn't have anything in it, it's going to return true. And then you can ask for the bag size, meaning how many items it has. And then you can use this add method to store a generic item in the bag. And then since a bag is an iterable collection, it's going to implement the iterable interface, meaning it will support this iterator method from the iterable interface. Okay, and that returns an iterator object that you can then use to enumerate or iterate over the elements of the bag. Right? You can, for example, use then the for each statement, okay, to iterate over a bag. Okay, so that's the API. It's rather simple. Let's now look at an example of a client program that makes use of the bag API to do something interesting. Okay? So what we're doing here is we first import a whole bunch of things. We first import linked bag, which is a particular implementation of this API. All right, and it's an implementation that uses a linked list as the underlying structure, so it's called a linked bag. Okay? But we'll look at that later on. So that's one thing that we import, and in addition we also import std in and std out. Those are 2 libraries of static methods. The program itself is called stats, and it's a client of the bag API, and let's see what it does. It has a single method, the main method. The first thing that we do is create a bag object using the constructor. Okay, and in this case we are creating the bag object such that it's going to store double objects of type double. Again, remember that generic, like data structures can only store objects. So here we are storing objects of type double with a capital D. This is a wrapper type for the primitive double. Okay. All right, and then what we do is from standard in, we read a whole bunch of primitive doubles using the read double static method from stdin, and we simply store that into the bag. So this is where we make a call to the add method in the bag API to store this particular item, in this case a primitive double, into the bag. And notice that there is auto boxing going on here because read double gets you a primitive double, but add can only take an object. But Java will automatically turn that primitive double into an object double and store that in the bag. Okay, and we do this as long as this stdin is not empty, and when this while loop is done, we have all the numbers from stdin stored inside of that bag. And then what we do is we just do some basic statistics, right? We first get the number of elements in the bag by saying capital N is numbers.size. So there we make use of this method from the bag API to get the number of elements in the bag. Then we initialize a variable called sum to 0, and we simply add up all the numbers in the bag. And how do we do that? Well, we make use of the for each statement, and we enumerate or iterate over the elements of the bag. Since bag is iterable, we can put numbers right there. It's an object of type bag, so it's iterable, and we are iterating over each and every double in that bag, and we simply accumulate that in sum. All right, and here again, remember, elements of numbers are double objects, but because of auto boxing, we are able to look at each element as a primitive double. Okay. So here there's auto unboxing going on. So each of these objects gets turned into a primitive, right? And that's what gets added to this variable sum. So once the loop is done, sum is going to store the sum of all the values in the bag. And then we calculate the average as sum divided by n, that's stored in mean. And then we initialize sum again to 0. And here what we do is we calculate the variance. So again, we go through the elements of bag using the for each statement, just like what we did here. And now we accumulate this quantity, x minus mean times x minus mean, right? So mean was calculated right here. Okay, so at the end of this for loop, what sum will store is the variance. Okay, and once we have the variance, we calculate the standard deviation as simply the square root of sum divided by n minus 1. And then at the end, what we do is we use formatted printing to print the mean and the standard deviation. All right, so that's what the program does. It reads a bunch of doubles from standard in, stores them in a bag data structure, and simply computes and prints basic statistics, such as the mean of all the numbers and the standard deviation. Okay, so we run the program as such by saying Java stats, and then we feed in a whole bunch of numbers via standard in, and put the end of file signal at the end when all the input is done, and the program comes back with the mean and standard deviation. Okay, so that's a nice little client program that shows how you work with the bag API. Okay, so now that we know about the bag API, and we've also looked at how you write a client program using the API, the next thing we need to discuss is how one implements the bag API. Right? And this is where we're going to look at two possible implementations. The first implementation is going to be using a linked list as the underlying data structure. And hence, this implementation of the bag API is called the linked bag implementation, right? Okay, so let's see how that works. So the implementation sits inside of a package, which is this, and then we import a couple of things. Okay, and here is the class declaration. So the name of the class is linked bag, and it's going to store generic types. So that's why we specify this item in angle brackets. Again, item is just a name. You could call it whatever you want, but then you just have to be consistent. If you call this let's say just capital T, then this has to be capital E and so on and so on. Okay, but here we just call it item. Okay, so linked bag is the data type, and that implements iterable because we want our bag to be iterable. Okay, all right. Now what do we have for instance variables? Well, for instance variables we have two things. We have this variable called first that is of type node, and what this is that it's the pointer to the first node in the linked list that's going to store all the items of the bag. Okay, so the underlying data structure for us here is simply a linked list. All right. Okay, and first is always going to point to the first node in that linked list. So that's this first. It's of type node. And then in addition, we also have capital N, which is simply going to store the number of nodes in the linked list. Now, since there is a correspondence between the items in the linked list and the items of the bag, this quantity N, which is the number of nodes in the linked list, is also the size of the bag itself. So N basically is keeping track of the number of elements in the bag. Okay, and then we have this private class that we saw before. That is our representation for a single node in the linked list. So each node stores a generic item, and it also stores a pointer to the next node. Okay, so that's that. So now let's look at the implementation of the constructor and the methods from the bag API. So the first thing is the constructor. It's called linked bag. And what we do here is just initialize the instance variables. Okay, so we set first to null because there's nothing in the linked list, it's just null. And we say n equals 0, meaning the linked list or the bag has no items yet. Okay. Now notice that this code is completely unnecessary because when you declare these variables here, these instance variables, they take on precisely these initial values. First is an object, so it takes an initial value of null. And n is a primitive int, so it takes an initial value of 0. But it's always good to be explicit and explicitly make these initializations in the constructor. Okay, so this just makes for readable code. Okay, so that's the constructor. Now let's look at the other methods. The next method is the isEmpty method from the API, and that's pretty straightforward. So how do you check if the bag is empty? Well, the bag is empty if the linked list is empty. If the linked list is empty, then the first has to be null. Okay, so we simply compare first versus null. So if first is pointing to a null, then the linked list is empty, meaning the bag is also empty. Another possible implementation could have been return n equals 0. That's fine too, because n simply keeps track of the number of items in the bag or the linked list. So if that is 0, then clearly the bag is empty. Okay, all right. What about the size method from the API? That's trivial. You simply return n because n keeps track of the size of the linked list or the size of the bag. Okay, and then we have the add method, and this is where we do something interesting. And here the code that you see is basically the code that we saw before for inserting at the beginning of a linked list. Okay, and that's what you see there. So you have a first that is pointing to the very first node, and then you have these other nodes. Right, and then what we are saying is we are creating a new variable called old first, which is pointing to what first was pointing to. So old first is also pointing to that. Okay, and then you say the new value for first is a new node. So now first is not that, but first is a new node. Okay, whose item is the item that you get as an argument. So this item is basically stored in there. Okay, and then you say the next guy of first, which is this fellow, is whatever old first was pointing to, well, which is that. Okay. So what do we have now? We have a linked list where we have created a new node at the head whose item is the item that was given as an argument, and whose next is the old linked list, right? And since we insert an item into the linked list or into the bag, we have to increment n by 1, so that n always reflects the number of items in the linked list or the bag. Okay, so that's how we implement add. Now, before we proceed, just keep in mind that this operation of inserting a node at the head of a linked list that has a size n is a constant time operation, and that's very important to realize. So inserting at the beginning of a linked list of size n is constant time, because there is no traversal or anything like that involved. You simply create a node and you make some pointer reassignments. So all this can be done in constant time. Okay, it does not depend on the current size of the linked list. The linked list might have 1,000 elements, it might have 1,000,000,000 elements, but this operation is constant time. Okay, so it's extremely efficient, and as a result, add is very, very efficient. So add itself is a constant time operation. Okay. Similarly, going back to what we talked about linked lists, even the other operations such as removing from the beginning and also inserting at the end, those are also constant time operations. Right? They simply do not depend on the number of elements in the linked list. Okay. All right, now, so while we are at this, let's also talk a little bit about the running time of the other methods that we have discussed so far. So add, as we just said, is constant. So I'll just write 1 for its running time. What about size? Well, size is clearly constant time. It simply returns n. So that's constant time. Is_empty is also constant time because it's a very simple comparison. Right? And then linked bag is constant too. Just two very simple statements. Right? So all these guys are constant time operations so far. Okay? Very efficient. Okay. Now, all that we have to discuss is how you make bag iterable. So now remember that a bag implements the iterable interface, which means you have no choice but to implement the single method that iterable supports, which is the iterator method. Right? So what do we do in iterator? Well, we return an object of type list iterator, which is defined right here as a private class, and list iterator implements the iterator interface. Okay, and all these things in angle brackets simply denotes that these guys are all generics. All right. Okay. Now, when we create an object of type list iterator, we pass a pointer to the first node in the linked list as an argument. Okay, and that's what you receive here. So this is what gets passed in, and you simply assign that to the instance variable current that is given here. So current is an instance variable of list iterator, and what is current? It's the current node that you're looking at in the linked list, the current node that you're enumerating in the linked list. Okay, so it starts at first. So that's the constructor of list iterator, and then has next is straightforward. All that you have to do is compare the current node versus null. If current is not equal to null, that means there is still some more nodes that you need to enumerate. But when current is null, then you know that you have enumerated all the nodes in the linked list, so you return false in that case. Okay. And finally, the next method from the iterator interface, that's pretty straightforward too. So the first thing that we do is check if there is a next or not by making a call to has next. And if there is no next to iterate, then we throw an exception, okay, saying there is no such element. But if there is something to iterate, then what we do is we get the item out of current and store that in a local variable called item, and then we update current to be the next node in the linked list. So we say current equals current.next, okay, and finally return that item from the previous current, which was stored here. Okay. So that's how we get hold of the next item in the linked list, starting from the very first node and going all the way up to the very end, right? and when until we reach the end, has next will always return true and return false precisely when current becomes null. Okay, and each call to next, as long as there is a next, it's going to return the item from the current node. Okay, and update current to be the next node. Okay, so that's our first implementation of the bag API using a linked list as the underlying data structure. So what we're going to do next is talk about yet another implementation of the bag API, but this time using just an array, all right, as the underlying structure. But it's going to be a resizing array, in that this array will grow or shrink over time. All right, it will grow when there is no room in the array to add a new item, and then it will shrink when there are fewer items in the few items in the link in the array than the capacity of the array. Okay, so in that case we shrink, and hence this implementation is called resizing array implementation. Okay, so let's see how this works. So we call the implementation resizing array bag. Again, it is it is a generic, so we put item and angle brackets. It's going to be iterable because we want bags to be iterable, and hence it implements iterable. Okay, and then this time around, for the instance variables, we have a static array called A of generic type, right? Item. So this this array can store objects of any type, but it's an array. It's not a linked list. Okay, and then in addition, it also has, just like before, a variable n that keeps track of the size of the array or the size of the bag itself. What do we do in the constructor? Well, in the constructor, what we do is we first initialize this array A. So we say A is simply an array of objects cast to the generic type. So that's just syntax that you need to remember. And then what's important is that we initially create this array with size 2. We just fix the size to be 2. So initially, this array can store up to 2 items, right? 0 and 1. So this is A. Okay, and then we initialize n to 0, meaning there are no items currently in the array or in the bag. What about is empty? Very easy, you simply compare n with 0. So if n is 0, it means that there is no item in the array and hence no item in the bag. What about size? Trivial, simply return the value of n, because n is going to keep track of the number of items in the array or the bag. And then what we have is a private helper method called resize, which is going to be responsible for resizing this array A to the specified capacity. All right. So this is the private method that we're going to use to grow this array, to make it bigger, or to shrink it, to make it smaller. Okay, so how does it work? Fairly straightforward. So you create a temporary array of generic objects, and you create it as an array of object cast to the generic type with the given capacity that's specified as an argument. Okay, and then what we do is, in this for loop, we simply copy the values from the array A, the old array, into temporary array. So I goes from 0 all the way up to n, where n is the number of items in the bag or the array. So we copy all those items into temp by saying temp at I equals A at I. Okay, so we just copy in all the items from A into temp, and then we say the new array A is simply whatever temp is. So now A has grown in size in size. So for example, if A started out with a capacity of 2, and then we make a call to resize with a capacity of, let's say, 4, then, and let's say, there were some values here, two items in there. So now, after this method is called, A is going to be resized to 4. All right, 0, 1, 2, 3, and then these values are copied in. All right, and nothing here. So these two guys are null. Right. So now, as you can see, after the resize operation, this has more capacity, so it can store more items. Okay, so that's basically the idea. All right, So now let's look at the next method from the API, which is the add method. So add method gets a generic item that you want to add into the bag, and you're going to store this in the array A. But before you store it, you need to make sure that there is room for that item in the array. Okay, and the way you check that is by comparing n, the current size of the bag or the number of elements actually present in the array, with the array's capacity, which you can get by saying a.length. So if these two guys match, that means there is no room in the array. Right? So in that case, you have to resize the array, and the way you do that is by calling this method with an argument that is twice the current capacity. So initially A had a size 2, so the first call to resize would be with a size of with a capacity of 4, and then the next time around resize is called, it's called with the capacity 8, and then 16 and 32 and so on. Okay. So whenever you run out of space in the array, you double its capacity. All right, and then once that is done, then you know that when you're here, you know that there is room for this incoming item. So you simply store it at the index n. You store item at the index n, and then you increment n by 1. Okay, so the way n plus plus works when it's used as an expression is that you first go with the value of n. So if it is used as an array index, if you say this equals some item, this item is stored at the index given by n in the array, okay, and then n is incremented by 1. Okay, that's the effect of a post increment. So item is stored at a at n, and then n gets incremented by 1. So this line of code is actually equivalent to these two lines. So it is as if you're saying a at n equals item, and then n plus equals 1, which is the same thing as saying n plus plus. Okay, so these two lines are equivalent to this line here. Okay, all right. Now here, what about the running time? What's the running time of the constructor? So it turns out that the constructor is actually constant time operation. You're just creating an array of size 2, which has a constant cost, and you initialize a variable which is constant time. IsEmpty is also constant time. You just have the simple comparison. Size is constant time because you're simply returning a value. Resize has a linear cost because you're performing n iterations, so that clearly has a linear cost. So the running time of resize is n. Right? What about add? Add is very interesting. Add, for most part, most of the time, a call to add only results in this statement being executed, and that has a constant time because you're just going to a particular location in the array and setting the item there. So that has a constant cost. But then every once in a while, resize is invoked, which has a linear cost. Okay, and when is resize invoked? It's invoked when when there is no room in the array, meaning the capacity of the array is equal to the number of elements actually in the array. Okay, so resize is called every once in a while. So the question is, what is the running time of add? Well, if you actually carry out a full-blown mathematical analysis of add, you will see that in the average sense, right, or in what is called the amortized, sense, the running time of add is actually constant. That is because we call resize, this linear operation, very rarely, or only once in a while. And the other thing is, when we call resize, we are doubling the capacity of the array, and because of that, when you do the analysis, you will see that the running time of add in the average sense is constant. Okay, so add is also constant, but in this amortized sense. Okay, so it's fairly efficient. That's the bottom line. Okay, now let's look at how you make this particular implementation of bag iterable. Well, it's the same idea. We had bag implement the iterable interface, which means we need to implement the iterator method, and there we simply return an object of type array iterator, which is right here, defined as a private class. An array iterator implements the iterator interface. Okay. So what are we doing here? Well, we say the current item that you're looking at or you're enumerating is I, and we set I to 0 in the constructor for array iterator. Okay? And then in hasNext, we simply compare I with n. Well, n was an instance variable inside of the bag, the resizing array bag. Okay? So as long as I is less than n, we say there is something to be enumerated. So hasNext returns true. And when I is precisely n, hasNext returns false. And what do we do in next? We'll check if there is something to be enumerated by making a call to this method here. And if not, it's an exception. Otherwise, what we do is we return the item at I, and then I is incremented by 1. Okay, so the first time around when you make a call to next, it's A at 0 that gets returned, and I becomes 1. The next time around, it's A at 1 that gets returned, and I becomes 2, and so on. So this return statement can also be thought of as in the following lines of code. So it is equivalent to saying item, let's say x equals A at I, and then you have I++, and then you have return x. So these 3 lines of code is equivalent to this single line of code here, right? Okay, so that completes the implementation of this resizing array version of bag. So we have 2 implementations of the bag API, one using a linked list and the other one using a resizing array. And both implementations are extremely sound, meaning every operation was implemented as efficiently as possible, right? So now what we're going to do is discuss our next fundamental or basic data structure, which is the queue, all right? So what is a queue? A queue is an iterable collection, and it is based on what is called the first in, first out policy. So what that means is the first item that goes into the queue is the first item that comes out. So for example, you could use a data structure like a queue to model a queue in a grocery store, all right? So it's the person at the head of the queue that is served first, and someone who joins the queue joins at the tail end of the queue, and so what we have there is the first in, first out policy, and that's very nicely modeled by a queue data structure. Right? So what you see here is the API for the queue data structure. You can and it's going to be a data structure that stores generic items, and you can build an object of type queue using the constructor, and it stores generic objects, and the constructor is going to build you an empty queue. And then once you have a queue object, you can check if it's empty or not. You can ask for its size. You can insert or enqueue an item into the queue. You can remove an item from the queue. All right. Now just keep in mind that you can picture a queue as follows, where the head of the queue is here and tail is here. Now when you say enqueue, you put something at the tail end of the queue, right? And when you dequeue, you remove something from the head side of the queue, right? So keep that in mind. And then since queue is iterable, you can call the iterator method on a queue object to get an iterator, all right? So that's the API. Let's now look at a client program where we make use of this API, right? This program is called readins, and we import a particular implementation of the queue API that uses a linked list, and we'll talk about this next. And then we also import std in and std out. And then in the main method, what we do is we build an empty queue object. And it's a queue of integer objects, meaning it stores integer objects inside. And then what we do is we read integers from standard in and simply stick them into this queue. So we say as long as standard in is not empty, read an integer from standard in and stick it inside of the queue using the enqueue method. Okay, and here again, remember there is auto boxing going on. This is the primitive int that gets turned into an object integer that is then stored in the queue. Okay, and then since queue is iterable, we can use a for each statement or an enhanced for loop to iterate over its elements. So we say integer I colon queue, which is iterable, and what we are doing is in each iteration we're simply printing out the value of I. And here there is auto unboxing going on because each element here is an integer object that gets turned into a primitive int, which is what gets printed out. Okay, a very simple client. And here is that program in action. We run readins, we give it a whole bunch of numbers in standard in, and then specify the end of file signal, and the program comes back with the same numbers and in exactly the same order. And it is basically the first in first out policy, right, in action. This was the first item that went into the queue. That's the first item that came out. The next item that went in, next item that came out. Last item that went in, last item that came out. Okay? All right, now the question is, how do you implement this data structure? So our first implementation, just like what we did with bag, it's going to be based on a linked list, right? So the underlying data structure is going to be a linked list. And this implementation has the name linked queue. It's going to store generic objects. It's iterable, so it implements the iterable interface. Okay. And then for instance variables, it keeps track of three things. N for the number of items in the queue or in the underlying linked list. And then two node pointers, one called first and the other one called last. Okay, so first is going to point to the first item in the linked list, and so on. First points to the first node in the linked list, and last points to the last node in the linked list, right? So that's these two guys. Now, and then we have our private node class that represents the linked list. We've seen that before. Now let's talk about the API itself, how you implement it. The constructor is fairly straightforward. We simply initialize these guys. Again, this is completely unnecessary because when you declare these variables here, these are exactly the values that they take on. N is 0, first is null, last is null. But as I said before, it's good to be explicit. Okay, so that's the constructor, and the running time is constant. Okay. Is empty is pretty straightforward. You simply compare first versus null. There are other ways to do it. You could have also compared n with 0, but this is perfectly okay, and this is also constant time. Okay? Size is trivial. You return n. That's constant time. What about enqueue? So enqueue, remember, we said that when you enqueue something, you stick it at the tail end of the queue, meaning here. And that's an operation that we discussed before when we talked about linked list. So that's basically inserting at the end of the linked list. Okay, so the code that you see here is almost identical to the code that we saw there, right? So we simply say or last is whatever last was pointing to, which is that guy, and then we say last is now a new node, and whose item is set to the given item. So this item simply goes in there. All right, and then we say last next is null, so that's simply null, right? And then what we do is somewhat interesting. So we say that if the queue is empty at this stage, all right, meaning if first is null, then we have to say first is equal to last. All right, and you have to do this because when you go from nothing for the linked list, meaning when the queue is empty, to having a linked list or queue with one item in it, just one node, then you have to make sure that both first and last point to that node, right? So you want first and last to point to that node. That's what we take care of there. Okay, so when you go from an empty queue or a linked list to a one element queue or a linked list, you have to make sure that first and last point to that node. Otherwise, what you do is you're sort of in the general setting where you simply say old last dot next is simply what last is. So old last was pointing to that, and we say its next, which was null to begin with, is now whatever last is. So this now points to this guy here. Okay, so that's what we're doing right here. And since NQ is inserting something into the linked list or the queue, we increment n by 1. So that's what this does, right? And now, what's the running time of NQ? Again, well, it's constant time because there is no traversal of the linked list inserted at this point. It doesn't matter how many elements you have in the linked list. What we are doing for NQ is simply adding something at the very end of the linked list, okay, without having the need to traverse it. So all this code, it's a constant time operation, right? So it's very, very efficient. What about DQ? Remember that when we do a DQ, we need to take something out from the head of the linked list, all right? Because only then we would be implementing the first in, first out policy, right? Okay. So we first check if there is something to be DQ'd. If not, it is an error, so we throw an exception. Right? Otherwise, what we do is we record the item in the first node. We store it in a local variable called item, and then we say the new first is first dot next. Okay, so it is as if you have something like this. And first points to that guy. So what we do is we grab the item in here and store it in this variable. So this item here is pointing to this guy here, and then we simply say the new first is first dot next. So first now points to that, right? And since we removed something from the linked list or the queue, we decrement n by 1. So that's that. And then here again, just like add, we have to be a little careful. When the linked list or the queue becomes empty, right, meaning when n becomes 0, then you have to make sure that last is null, right? So we need this particular line of code, right? So this just makes sure that when the linked list or the queue reduces to nothing, last is correctly pointing to null, right? And at that stage, even first will point to null. And then finally, we simply return the item that was saved away in this variable, because DQ needs to return that item. Okay, and so that's how you implement DQ. What is the running time? Here again, it's a constant time operation. Why? Because the way we implement DQ is by removing an item from the beginning of the linked list. Okay, and that does not involve any traversal. It's a constant time operation. Right? It doesn't matter how many elements you have in the linked list. Okay, so last bit then is to talk about how you make queue iterable. Well, we implement the iterable interface, which means we implement the iterator method by returning an object of a type called listIterator, which is right here, that implements the iterator interface. And we pass a pointer to the first node as an argument, which we receive here, and assign to the current instance variable, which is this guy. All right. Has next is pretty straightforward. We simply compare current versus null. If current is not null, that means there is more to be enumerated from the queue. And next is pretty straightforward too. We first check if there is a next. If not, we raise an exception. Otherwise, what we do is we grab the item from the current node, store it in a local variable, and then update current to be the next node, and then finally simply return the item. Okay. So that's how we make queue iterable. And notice that this implementation of list iterator here is identical to what we had for list iterator in the implementation of the bag API. Right? In the first implementation that we saw, that used linked list as the underlying structure. It's identical. Okay. Now the next thing to talk about is yet another implementation of the queue data type, but this time using a static array. All right? So this implementation is called Resizing Array queue. It is a generic, so it's going to store objects of any type, and it is iterable, so it implements the iterable interface. So what do we have for instance variables? Well, we have a static array called queue that is going to store the items in the queue. We have n to keep track of the number of items in the queue, and then first and last, which are going to be the indices of the first and the last item in the queue, right? And these are indices into this array queue. What are we doing in the constructor? Well, we initialize, we create the array queue as an array of generic items, and we set it to be of size 2 to begin with, just like what we did with the resizing array implementation of bag. And then we initialize n first and last to be zeros. Okay. And then and the running time of the constructor is constant, right? Okay. What about the isEmpty method? It's trivial. You simply compare n versus 0, and then size simply return n. And both of these methods are also constant time operations. And then we have a private method called resize, quite similar to what we saw with, in the case of the resizing array bag. And what are we doing here? We create an array called temp of size max, which is the given capacity. And then what we do is we simply copy over the elements from queue into the array temp, right? And then we say queue, the new value for queue is whatever temp was pointing to. So now queue is a resized array, okay, with all the old values copied in. Okay, and then finally we say first is 0 and last is n. So first is basically pointing to the 0th element in the array. Its index is 0, and last has an index n, which is where the next item would go. Okay. Okay, so that's the resize method, and that has a running time of n because of this loop here. Okay. Okay, so what about the enqueue method now? Well, what we first do is we check if the number of elements in the array is equal to the capacity. If that is the case, then it means that there is no room in the array for the incoming item. So we have to resize the array, and that's what we do by making a call to that private resize method, giving it an argument that is twice the current capacity. Okay, and then we simply say queue. The last item in the queue is simply item. So we store item at index last, and then we increment last by 1. So notice the post increment, very important. Okay, and then we say if last is exactly the capacity of the queue, then we set last to be 0. Okay. And then since we are inserting something into the queue, we increment n by 1. All right, so that's that. And let me just say something about this conditional here. So if last equals queue.length, then by saying last equals 0, we're sort of making this into a circular queue. All right, so just keep that in mind. So that's what is going on there. Okay, and what is the running time of enqueue? Well, all these operations are constant time operations, the only one that is not a constant time operation is this call to the resize method that we just said is a linear time operation, but that is only called once in a while, all right, when this condition is true. And then when that happens, we are resizing the array to twice its current capacity. So here again, if you do a proper analysis of this method, you will see that it is constant in the amortized sense. Okay. All right, what about the dequeue method? Well, here we first check if the array is empty. If so, we say it's an error. We throw an exception because you cannot dequeue an empty array, empty queue. Otherwise, what we do is we grab the item from the head of the the head of the queue, which is the first item in the array. So we say queue it first is the item. Okay. So item is simply the element given by the index first in the array, and then we say queue at first equals null, right? And then since we are removing something from the queue, we say n minus minus, the number of elements has gone down by 1, and then we increment first by 1. Okay, so the first now points to the next element of the array, and then here we check if first equals the capacity of the queue, right? So this is similar to what we did here by comparing last with the capacity of the queue. And if that is the case, we say first equals 0. So this again makes it into a circular queue. Okay, and then the last bit is to check if the number of elements in the array is significantly less than the capacity of the array, in which case we shrink the array by a half. Right? So what we're saying is if the number of elements is greater than 0, meaning it has at least one element, and if the number of elements is equal to the capacity over 4, meaning it's at the quarter of the capacity. If that is the case, then we shrink the array to half of its current capacity, okay, just so that we don't waste space in memory. Okay? So here we are shrinking the capacity by a half by calling the private resize method. Okay? And finally, we return the item that was saved here. Okay? So what is the running time of the dequeue method? Well, here again, most of the operations are constant time except for this call to resize, but that happens only under this condition. Okay? So here again, the running time in the amortized sense is a constant. Okay? And then the last bit is talk about how you make this implementation of queue into an iterable construct. Well, here's how you do it. You have it implement the iterable interface, which means you need to implement the iterator method from that interface, and we simply return an object of type array iterator, which is right here as a private class that implements the iterator interface. And the single instance variable inside of it, array iterator is I. That's the index of the current item that you're enumerating. We initialize that to 0 in the constructor, and has next is trivial. You simply compare I with n. So n is an instance variable in the resizing array queue. So as long as I is strictly less than n, it means that there is something more to be enumerated. So has next returns true. Okay, and then next we first check if there is a next. If not, it's an exception. Otherwise, what we do is we grab the item at index I, and we store it an item and simply increment I by 1 and finally return that item. And we do this modulus business again because our queue is circular, right? And this arithmetic takes care of, make sure that you're looking at the right element and that you sort of turn around at the right time, okay, at the right point. Okay, so that's another implementation of the queue API, but using a static array, right? So we're done with queues, and the last data structure, last fundamental data structure to consider is the stack. So what is the stack? The stack is an iterable collection, just like the bag or a queue that stores generic items in it. And it is based on the last in first out policy, right? Or LIFO for short. So the last item that goes in is the first item that comes out. So that's how a stack works. So what you see here is the API for the stack data type. So you can build a stack object using the constructor, and it is a stack of generic items. Then once you have a stack object, you can check if it is empty or not. You can ask for its size. You can push an item on top of the stack. Then you can peek at what's on top of the stack. So peek tells you what is on top of the stack, but it doesn't affect the stack. It doesn't remove that item. Okay. Whereas pop removes the top item from the stack and gives it back to you as a return value. Okay. So pop is quite different from peek. Pop modifies the data structure, whereas peek does not. And then, since stack is iterable, you can get an iterator out of it. Okay. So now let's look at a simple client that makes use of the stack API. So this program is called Reverse. We implement a particular implementation of a stack that uses a linked list as the underlying data structure. So this is called link stack. And then we also import two libraries, std and an stdout. And then in the main method, in Reverse, we build an empty stack as a stack of integer objects. And then from standard in, we read in a whole bunch of integers and store them in the stack. Okay, so here again, remember there is auto boxing going on, which turns this primitive integer into an integer object that gets pushed on top of the stack. And then finally, what we do is we enumerate the stack. Stack is iterable, so you can use the enhanced for loop to enumerate its items, which is what we're doing here, and we print each item out. And here again, there is auto unboxing going on. Each integer object is turned into a primitive which gets printed out. Here is how the program behaves when you run it. So if you say Java reverse and hit enter, then the program expects standard in. Let's say you type all these numbers and send the end of file signal. The program comes back with this output. And notice that the last item which went in is the first item that comes out. The second last is the second that comes out. Okay? The third last is the third that comes out. And the first item that went in is the last that comes out. So this is the LIFO policy that we discussed here. Okay. All right. So now let's talk about how you implement the stack data type using a linked list first. So the implementation is called link stack. It stores generic objects, and it implements the iterable interface. For instance variables, it has n to keep track of the number of items in the stack, and simply a pointer to the first node in the underlying linked list, right? And then we have our private class node representing the linked list itself. The constructor simply initializes these two guys. That's a constant time operation. Is empty compares first with null, constant time. Size simply returns null, that's constant time. Now push, what we do is we simply insert something at the head of the linked list. Okay, so we have our linked list that looks like that. And first is pointing to the first node. So what we are saying here is when we are pushing an item on top of the stack, we simply insert that item at the head of the linked list. All right. So we are treating this side of the linked list as the top part of the stack. Okay. So when you push on top of the stack, it goes right here. So what are we doing? We say old first points to whatever first was pointing to, and then we say first is now a new node whose item is the given item. So that's this line here. So this item now goes in here. And then we simply say first's next is whatever old first was pointing to. So this establishes this pointer. Okay. So now we have a linked list whose first node has this as the item. Or in other words, this item is now on top of the stack that is represented by this linked list, right? And since we are adding something to the linked list, we increment n by 1. So what is the running time of this operation? Well, it is constant, because as you can see, it simply involves sticking something at the head of the linked list, and that's a constant time operation that does not depend on the number of elements in the linked list, okay? And there is no traversal or anything like that involved. The next method from the API is peek, and that is pretty straightforward. We first check if the stack is empty, and if so, report an error. You cannot peek an empty stack. Otherwise, we simply return the item that is sitting inside of the first node. Okay, and notice that peek only tells you what is on top of the stack. It does not remove it or anything like that. Okay, and this is a constant time operation. What about pop? So the first thing that we do is check if there is something to be popped. Otherwise, if not, it's an error. Okay, so that's this line here. But if there is something to be popped, then we get the item from the first node. Remember it in this local variable item. And then we update first by saying the new value for first is whatever the next item is. So first is first.next. Okay. And then since we are popping something from the stack, we decrement n by 1 and simply return the item that we remembered. Okay. And what is the running time of pop? Well, it's also constant, because the way we implement this is by removing something from the head of the linked list, right? Removing from the beginning of the linked list. And that's a constant time operation. What about iterator? Well, with an iterator, we simply return an object of type list iterator, which is this guy here, giving first as an argument, which simply is assigned to the instance variable current, which is this fellow here, right? And has next compares current versus null. So as long as current is not null, we return true. When current is null, we return false. Next, first checks if there is a next. If not, throws an exception. Otherwise, we grab the item sitting inside of current, remember it in item, and then update current to be the next node by saying current equals current.next. And then finally, we return item. Okay. So that completes the implementation, the linked list based implementation of the Stack API. So the next thing that we're going to look at is an array based implementation of the Stack API. And here it is. It's called Resizing Array Stack. It stores generics in it, and it is iterable. Okay, so resizing array stack of generic items, implementing the iterable interface. For instance variables, we have a static array A, and then n to keep track of the number of items in the array or the stack. And then in the constructor, we initialize A, we set up the array A as an array of size 2, and it's an array of generic items. And then we say that n is 0 to begin with, right? So this is a constant time operation. Is empty is trivial. We compare n versus 0. That's constant time. Size simply returns n. That's also constant time. Resize, we've seen before, it has a running time that is linear. So what are we doing here? We are creating a temporary array with the given capacity. We copy out the elements from A into the temporary array, and we make A now to be the new array. Okay, A is now whatever temp was pointing to. Okay, what do we do in push? We first check if there is room for the new item. If not, then we resize the array to twice its current capacity by calling this private resize method. And then we say that the nth item in A is simply the given item, and we increment n by 1. So notice again the post increment. Okay, what is the running time here? Absolutely constant. Well, I shouldn't say absolutely constant, because of the resize operation. So it's constant in the amortized sense. So let me make a note of that. So every once in a while, resize gets called, right? Okay, moving on, let's talk about pop. So we first check if there is something to be popped. If not, it's an exception. Otherwise, what we do is we grab the item at n minus 1. Okay. Remember that n points to the n is the index where the next item will go. So the last item is sitting at n minus 1. So that's why we say item is a at n minus 1. Okay, and that's the item that we will eventually return. And then we say that at that location now we have a null. And this line is important. So this is what takes care of the loitering issue. Okay, because at that location you might have a reference to a giant object, such as like a huge like an image or a movie or whatever. And without this assignment, what you have is something pointing to a ton of something that is taking up a lot of memory. All right, and by making this assignment, setting that element to null, what you're doing is you're getting rid of that, you're reclaiming that memory space via the garbage collector. All right, so this line is extremely important. So I hope, let me mention that once again. So this item a at n minus 1 that you're popping might actually be a pointer to some giant blob of memory, right, taking up a ton of space. Unless you say a at n minus 1 equals null, there is a pointer to this chunk of memory, so that is not released for you. Okay, though you have, you're sort of thinking of that thing as being popped from the stack, right? So this line is extremely important, a at n minus 1 equals null, which is what ensures that there is no pointer to this blob of memory, which then eventually gets garbage collected. Okay, so it's this assignment that avoids this problem of loitering. Okay, and then since we are taking something off the stack, we decrement n by 1, and then finally we check if the number of elements in the stack is quarter of its capacity, in which case we shrink the array to half of its current capacity. Okay, and then finally return the item that we remembered here. Okay, so that's pop, and here again the running time is tfn equals 1 amortized, because every once in a while we make a call to the resize method. Okay, what about peak? We first check if the stack is empty. If so, we raise an exception. Otherwise, we simply return the value that sits at location n minus 1, because that is the top of the stack. Okay, that's the element that we are considering as being top of the stack. Okay, and the last bit is turning the stack into an iterable construct, and the way we do that is by implementing the iterable interface, which means provide an implementation for iterator, and what we do there is return an object of type reverse array iterator, which is right there, that implements the iterator interface, and the single instance variable that it stores is I. And the implementation is very interesting. Notice, we don't call it array iterator, but we call it the reverse array iterator. Why? Because this is an iterator for a stack, and it needs to enumerate the stack from top to bottom, right? And hence the name reverse array iterator. Okay, and notice how we initialize I. We initialize I not to 0 here, but to n minus 1, right? And what is the item sitting at n minus 1 in the array A? Well, that's the top of the stack. That's the last thing that went in, right? So I starts at that item. And then has next compares I with 0. So I is going to start at n minus 1 and going to be decremented constantly, right? And at some point it's going to hit 0, which is when has next will return true. Which is when has next will return false. So as long as I is greater than or equal to 0, it's going to return true. Okay, and then in next, we first check if there is a next, and if not, throw an exception. Otherwise, what we do is we return the value at I, and then we post decrement it by 1. Okay, so this line of code is equivalent to saying item x equals a at I, and then I minus minus return x, right? So these 3 lines of code is equivalent to this single line of code. Okay, so that completes the implementation of the Stack API in 2 different ways, one using a linked list and the other using a resizing array. So the last bit in this lecture is to talk about the performance characteristics, which we already have a pretty good handle on. So in the linked list based implementations of the bag, queue, and the stack API, all operations take constant time in the worst case. Right? So they are all extremely efficient. Every single operation is a constant time operation. What about the resizing array based implementations of the bag, queue, and the stack API? Well, there again, the implementations are all extremely efficient and they're all constant, but with some of the operations, they're constant in the amortized sense. So for example, the push and pop in the array based implementation of stack, it's constant in the amortized sense, all right? Because every once in a while you make a call to the resize method, which is a linear time operation. But that's okay because you call resize very rarely, right? And when you do a proper analysis, you find out that in the amortized sense, even methods like push and pop in the array-based implementations, they have a constant running time, all right? So that concludes our discussion of these basic data structures, bags, queues, and stacks. So we have looked at different implementations of these data structures, first using a linked list and then using a resizing array. And our implementations have been extremely robust and efficient. All right. So we have implemented them in the best possible way. Okay. So that's the end of the lecture, and thank you for your time.